Okay, now we're going to talk about the relationship between free energy and equilibrium. So standard delta G determines the spontaneity of a reaction under standard conditions, and the equilibrium constant determines how far a reaction will go towards the products. So there's going to be a relationship between the size of K and the size of delta G. If K is large, we're going to have a more negative delta G because the products are favored. If we have a small K, we're going to have a more positive delta G because the reactants are favored.
I heard that they finally found the cause of long COVID brain fog.
Oh, did they?
Apparently.
What is it?
I don't remember. What was it? You can look it up. That's too much science, and
That's
I'm
okay.
still recovering from a car
That's,
crash.
well, yeah, you got brain fog. So
Exactly.
how could you be expected
I
to
have
remember
brain fog,
this?
but just not the COVID type.
Okay, so this is the equation that we would end up with. Delta G is equal to negative RT natural log of K. We're going to skip that one because I don't like that one either. Here, calculate standard change in Gibbs free energy. Delta G equals negative RT natural log of K. We're given the equilibrium constant. So, like on an exam, how are you expected to know what to do with this question? Well, honestly, here you have delta G0, Rxn, and you've got a temperature and you have a K. And what I would do is I would go look at the page of equations that I give you, and I would try to find one that had those things in it. Seriously. And so there's only one, and it's that guy. Any questions? This equilibrium constant is kind of big, right? It's definitely greater than 1, which tells us that products are favored. And so delta G here is negative. It's spontaneous. This is actually going to go forwards. So this is the one we just looked at. But the free energy change depends on temperature. So we can combine these two guys together. And, that's just not very useful, is it? I'm feeling a little jaded today. And I'm finding my notes here to be just kind of sketchy. So there we have an equation that relates stuff. You can take that equation and rearrange it and get this. I just don't want to. So you can get that guy. This is the straight line form. So here we could plot the natural log of k versus 1 over t. 1 over t is x, natural log of k is y, and we're going to get a straight line, and we can find the equation, and the slope is equal to negative delta h over r, and the intercept is delta s over r. Now, does that sound a little familiar? Yeah, we had an equation earlier that took the same form, right? The letters are different, but the idea is exactly the same. So here we could calculate k based on t, or we could measure k at different t's. And then we could find out what delta h and delta s are, because those are the ones that are hard to figure out. Technically, this is limited temperature range. So you don't want to go too crazy on the temperature. And then you can take that and make a 2-point form, which we also saw in one of these earlier with the other similar equation. And the beauty of this one is we can find delta H, the standard enthalpy change for a reaction, by measuring the equilibrium constant at 2 different temperatures. Just 2 different ones, instead of doing a whole bunch and making a graph and a line and everything. Now that's going to be better, but sometimes you don't have that option. So we can use this to calculate delta H. If we know what delta H is, and we know the equilibrium constant at 1 temperature, we can use this to calculate the equilibrium constant at a different temperature.